Perfect. Okay, thanks for coming, everybody. I'm Cunillera, and today I'm going to talk about phase space reconstruction of semiconductor laser dynamics using reservoir computing. Okay, let's think that we are, for example, experimental physicists, and we are measuring the variables of a nonlinear system, which is described by a dynamical system. And we may face some kind of problems. For instance, one sensor stops working, so we can't measure that variable anymore. Or we can even run out of time, and so we cannot do any more measurements. And okay, the question is, can we overcome this kind of data availability issues? We're going to work on two different scenarios. The first one, we have an infinite time series of measurements for one of these variables, and a finite time series of measurements for all the remaining variables of the dynamical system. And we aim to infer the time series for these later variables beyond the time that we don't have more measurements. And in the second scenario, in this case, we have a limited time series of measurements for all the variables of the system, and what we aim is to predict the time series. Okay, in this work, our objectives are, we use a machine learning technique called reservoir computing, and the available data in these two scenarios to implement a state observer, which will help us to infer time series or to predict time series. We're going to test these algorithms on a three-dimensional nonlinear dynamical system, which is the model for a semiconductor laser. And for the prediction algorithms, we will compare them with an approximate mathematical model for the laser. And we want that our algorithms, they must be able to outperform the mathematical prediction system, and we want to extend the prediction horizon of our methods. Okay, let's talk a little bit about the methodology. Here we can find a scheme of the time series inference algorithm. Here we have a reservoir, which is a random neural network whose nodes evolve nonlinearly. Here U is the time series for which we have an unlimited time series of measurements, and we project this time series into the reservoir nodes. We project this via map, and what we aim is to make the nodes evolve so that when we project the states of the reservoir R that we have been storing, we want to project them so that it reproduces the behavior of the variables that we want to infer. And to do so, we can project the states of the nodes. And in this projection, we have a lot of free parameters that we can compute by doing a linear regression between the time series for these measurements that we have and the reservoir state. Okay, this is the autonomous reservoir computing predictor algorithm, which works more or less, it's very similar as the cross prediction algorithm, although here we feed the reservoir with the whole set of measurements that we have, and what we aim to reproduce is the values of the variables at the next time step. And we do the same computation of parameters here, and when we run out of time series here, then what we do to do prediction is to use a feedback loop of the reservoir output as the reservoir input. And then the hybrid model, which is a modification of the previous one, in which we include an approximate mathematical model. In this case, we use a mismatch in one of the parameters. And this mathematical model takes the input variables, it produces an initial guess of the prediction, which is mapped to the reservoir with the input variables, and it's also projected with the reservoir states to produce the prediction. And okay, now I'm going to talk about the model that we are studying, which is a a three-dimensional nonlinear dynamical system, which stands for the model for an optically injected class B semiconductor laser. It has three variables. This is the carrier density, N, and this is the complex electric field, E, which can be described in terms of the real and imaginary part of the field, or its amplitude and phase. Well, why did we choose this model? Okay, we have a laser. We can easily measure the intensity of the field, which is the square of the amplitude of the field. We can measure it in real time quite easily, since we only need a fast oscilloscope to do so. But to measure the phase and carrier density is quite tricky, and we would need to use a technique called phase-based tomography, and it's much more difficult. And okay, this model has 5 parameters, and we can tune 2 of them experimentally, which are the gain K and the detuning omega. And this model also shows a rich variety of dynamics. If we change these 2 parameters, we can find up to 6 topologically different dynamical regimes. And I show them in this slide. These 2 show bounded phase dynamics, and these 4 unbounded phase dynamics. This is a stationary fixed point. This is a periodic dynamics, also this one. This is period 3 dynamics. This is quasi-periodic dynamics. And here we can see in this trajectory in the phase space a strange attractor, which corresponds to chaotic laser dynamics. And well, now I'm going to show some results of the cross prediction algorithm. Here, in all the figures that follow, in blue I've represented the real-time series that I have obtained by integrating the model. And in red dashed lines, I represent here the prediction or the inference, or the predictor or inferred time series. In this case, they are inferred time series by using the cross prediction method. And this is in the chaotic laser regime. I use the real part of the field as the input variable, and then I manage to infer the time series for the imaginary part of the field and the carrier density, as you can see, very accurately. The same can be said when using the imaginary part of the field as the input variable of the reservoir and the carrier density. However, if we use the amplitude and phase description of the field, and we try to infer the phase when using either the amplitude or the carrier density as the reservoir input, we did not manage to infer the dynamics of the phase accurately. Why does it happen? Because the phase is not bounded in 4 of the 6 dynamical regimes. What we did to overcome this is to use a finite time phase, which is defined at time t as the phase minus the phase at the previous time step. And here we can see in the quasi-periodic regime that we can, in fact, reproduce the dynamics of the finite time phase accurately. And the same in the chaotic laser regime for the amplitude and finite phase. When using the amplitude as the reservoir input, we can reproduce the dynamics of the other 2 variables accurately. Also when using the finite phase as the reservoir input, and when using the carrier density as the reservoir input. Okay, just a moment, please. Now I'm going to present some results and conclusions about the cross prediction method. One of them is that we can use this method for reconstructing the dynamics of the semiconductor laser in any of the dynamical regimes in an accurate way, and using any dynamical variable as the reservoir input, and in any description of the electric field, although we had to use this finite time phase when the dynamics is unbounded in the phase. Then we found that even though we can use any input variable, the accuracy of the of the method does not depend on which the input variable is. All of them, we can achieve good results and accurate with any input variable. And we also studied in the master thesis manuscript that the dependence of the accuracy of this method on the algorithm parameters. For instance, the dependence of the accuracy on the size of the reservoir, which is the number of nodes that it has. The larger the reservoir is, the more accurate results we get, although the time that it takes for the algorithm to run, it's much higher for large reservoirs than for small reservoirs. And when we add small Gaussian white noise to the time series, we found that this method is quite robust, but when only under small noise. Now let's talk about reservoir computing prediction results. Here we can see a sketch of the time series, the predicted time series, when using the autonomous reservoir computing predictor. Here we can see here that for the real and imaginary part of the field and the carrier density, that the dynamics is predicted accurately, although up to a certain time step, beyond that time step, the dynamics is no longer reproduced accurately. What does it happen? Okay, I plot here in black the error that is produced when the error between the predicted time series and the real time series. And when it exceeds a certain threshold, we define that it's no longer accurate, and at this time is the prediction horizon beyond which our dynamics is no longer predicted accurately. And take in mind the prediction horizon as I've defined now, and let's compute it for the hybrid scheme, the autonomous reservoir computing predictor, and the mathematical model. Okay. This mathematical model follows the same equations that I've integrated before, but if for obtaining the true time series, we used the alpha parameter equals to 2, then I introduce a mismatch in this parameter in order to make it approximate. I introduce a mismatch of 0.5, which is 2.01, of 5%, 2.1, and up to 50%, alpha equals 3. And the same mismatch is introduced in the hybrid predictor. That's to say, we introduced in the approximate mathematical model of the hybrid predictor this mathematical model, but with the mismatch. And then these are results of the prediction horizon with respect of the size of the reservoir. Here in black, I plot the results for the hybrid predictor, in blue for the autonomous reservoir computing predictor, and in red for the approximate mathematical model with that mismatch. This is for alpha equals 2.01. And well, we can see here that for small reservoirs, the autonomous reservoir computing predictor does not produce long, accurate predictions, but the hybrid predictor does produce good and long and accurate predictions for small reservoirs, so it can achieve good results faster than the autonomous predictor. But when the reservoir is large enough, then these two reservoir computing prediction methods are comparable. And if we increase the mismatch, we can see here for 2.1 equals to alpha, and for alpha equals 3, that the mathematical model accuracy goes down quickly, although the hybrid predictor does not depend so much on the mismatch on its internal parameter. It's quite robust under changes on the mismatch. And well, I'm gonna do some conclusions about the predictor methods. Well, the hybrid predictor can be used to achieve long and accurate predictions up to 6 Lyapunov times. even when the reservoir is small, so it's faster than the autonomous predictor, which was only comparable in terms of accuracy and length of the prediction with the hybrid predictor, only when the reservoir is large. And as I have stated before, the hybrid predictor does not seem to depend so much on changes on the mismatch that is introduced in the mathematical model that's inside it. And both methods may outperform the approximate model, provided that the reservoir is large enough. And then, just to finish, some future applications. It would be great to see a real-time implementation of these algorithms. Then, I think that, well, people here have worked on chaos-based cryptography based on laser synchronization. And if we can use the cross-prediction algorithm to reproduce the dynamics of a particular laser, we can compromise the security in this cryptography system. These methods can be used, or could be interesting to be used in data science for reconstruction of time series and for data recovery. And for example, in control engineering, the cross-prediction method is a nonlinear dynamic state observer, which is great. And well, the prediction methods could be used to increase the prediction horizon in forecasting. And that's it. Thank you, and thanks for coming again.
We'll take some time for questions.
Okay.
And if anyone wants to leave the room, can you stop? No. Anyone else? So maybe we can start listening. I didn't mention, of course, the supervisor of the work.
Oh, yeah. Sorry.
Is related to the figure 1 you presented in your thesis.
Okay, just a moment.
It is the map of the parameter space.
Yeah.
And then the table before table 1. They, at the first sight, they look not exactly correlated, let's say. Do they represent the same model or not?
What?
Because, I mean, there are points in the K omega space that are outside the table